Welcome to another edition of Tales of the Workshop. Today, we're going to feature how to create electricity, specifically direct current. Now, we're going to be using this machine right here. It's called a direct current machine, and we're going to see what are some of the mechanical aspects or the construction of this machine that's going to allow us to create electricity. Please stay tuned for this next session. I guarantee you it will be interesting. Here in this illustration, we actually have the electricity triangle. The electricity triangle is composed this way because we need all three of these items in order to create electricity. First off, we're going to need magnetism. Now, magnetism can either be naturally occurring, such as a permanent magnet, or it could be artificial, as in the case of using field windings or an electromagnet. We're also going to need a cutting action. Now, the cutting action is basically mechanical force. Now, the mechanical force can either be rotating or it could be linear, such as a piston action, as well as turns of wire. Michael Faraday did an awful lot of studies on the concept of induced voltage, and we need turns of wire in order to create electricity. And so this is the fundamental basis of having the electricity triangle. Now, what we're going to do is explore the mechanics of how a DC machine is built in order to create electricity. Looking at the body of the dynamo, what we can see is that there's four distinct pole pieces. Now, the pole pieces are made out of a ferromagnetic material or iron that has a high iron content, and as we discussed previously, we use ferromagnetic materials because it helps concentrate and raise the magnetic flux. Now, we have two sets of windings. The one winding closest, and I don't know if we can see that, but you should be able to see two sets of windings. The one winding set closest to the pole piece is called the series winding, and it's wired in series with the armature. The one on the exterior is called the shunt winding. Now, the shunt winding can be excited or separately excited from its own power source. Now, I mentioned earlier that magnetism could either be naturally occurring or it could be created artificially. And this is what we're talking about, is that by wrapping a coil of wire around a ferromagnetic pole piece, and if I was to run voltage and current through that winding, I'm actually going to have a magnetic field that's created. And because of the fact it's wrapped around the pole piece, the flux density of that magnetic field is going to be greatly increased. Now, pole pieces always have to be set in pairs. In this case, I have a 4-pole dynamo, meaning I've got a north and south polarity, as well as a north and south polarity here and here. Now, the relevance of the number of poles inside of a machine is directly attributed to the speed of the cutting action. If I had a 2-pole machine, then the machine that is going to provide us with a mechanical turning force or that cutting action is going to have to turn that much faster. By having a 4-pole machine, I'm basically going to be able to run the machine that is providing us the mechanical power that much slower. In the case of a windmill, windmills don't turn very, very quickly, and that results is that we would have to have a generator that has many pole pieces in order to get the right voltage. In our case, we're shooting for a voltage of 120 volts. That means then that I have to work out the speed that the cutting action is going to have to produce in order to get the 120 volts. A higher pole machine means that I don't have to turn it as fast in order to get the proper voltage. Now, what about the number of segments on a commutator? So, looking at our armature, this is a fundamental component that makes up the dynamo. We mentioned in our electricity triangle that we needed turns of wire in order to induce a voltage into them. Well, this is where the turns of wire come from. These are wrapped around an iron core. Why do we use iron? Well, it helps concentrate the magnetic field and will produce a higher output voltage if we use a stacked iron core with the turns of wire wrapped around it. Now, you'll notice that the turns of wire all end up right here at this device. Now, we call this the commutator, and this acts almost like a mechanical bridge rectifier, is that we want to produce direct current. In order to produce direct current, we need a method of taking the voltage that's produced here, which is fundamentally alternating current, and we have to convert it into direct current. And that's where the commutator comes into play. The commutator, well, we're going to have carbon brushes that will touch the commutator and will actually act as a conduit to direct the electricity to a circuit. In addition, we've got at opposite ends here bearings. The bearings serve to help center the armature within the housing of the dynamo. And in industry, we've actually come up with terms for them. This bearing in particular is called the drive-in bearing, due to the fact it's closest to this pulley. Down here, we have the opposite drive-in bearing. Now, it's important they have their own distinction due to the fact, and it doesn't apply to this particular armature, but in certain machines, the bearings are of different construction and of different diameters. So it's really important they have their own distinct nomenclature so that we can accurately identify them. And we also have the pulley. We had mentioned in our electricity triangle that we needed to have a turning force or some sort of mechanical action that will turn the armature so we can induce a voltage into these windings. And that's where the pulley comes into play. Now, the number of segments found on this commutator, and if we look very closely, we can see that each of these sections is a little copper bar. Now, why we have many sections on this commutator is due to the fact that we want to produce a waveform that is of sufficient quality. And what I mean by that is when I want to produce a direct current waveform, I want to have a nice straight line as flat as I can get it with the least amount of ripple. Now, I'm going to go to the whiteboard so I can demonstrate this a little bit more effectively. So what's the story with segments on a commutator? Here in my right hand, I've actually got the armature out of a different machine, and you'll notice that the commutator has not as many segments and that the segments are really distinctive. Over here in my left hand, I've got a smaller armature and that the commutator has got many, many segments in it. Now, what's that going to look like through the lens of an oscilloscope? Well, let's have a look here on the whiteboard. Here on the whiteboard, I'm trying to represent what we would look at through the lens of an oscilloscope, where we have a zero baseline, and this represents the amplitude of the waveform. Now, with direct current does not go in the negative, but it is positive. Now, when we have a commutator with very few segments, the waveform is going to look an awful lot like this, where we've got a series of bumps, and they never cross past zero, but there are definite peaks and valleys. And this is not a high quality waveform. Now, if we were supplying power to a DC motor, this will work just fine. But what about electronics? Most electronics operate on direct current, and they're sensitive to the quality of the electricity they get, specifically the voltage. Now, over here, if I was to look through the lens of an oscilloscope, I have many more segments on that commutator. I'm going to have a waveform that has much less in terms of peaks and valleys, and we call this a ripple. And I want to see a lower ripple, meaning that the deviation between the peaks and valleys could be less than, let's say, plus or minus 5 volts. So feeding sensitive electronic equipment, we require something that is going to produce a higher standard or quality of waveform. And it's rare in our trade to talk about quality of electricity, but that doesn't mean that it's not of major concern. So let's move on to other aspects of the dynamo's construction. So we're going to look at the inside of this machine, specifically right here. We've got what we call the commutator, and the commutator connects all the different turns of wire to the external circuit. Now, you'll see that we have many segments on the commutator. That allows us to create the direct current. So this is a DC generator, or otherwise known as a dynamo. Now, the dynamo, in order to create a DC waveform, actually has to have a commutator, and it acts almost like a mechanical bridge rectifier, where it's going to provide us with direct current. Now, the connection to the external circuit is done via a set of brushes. The electricity is sent to the external circuit via a set of carbon brushes. Now, the carbon brushes ride on top of what we call a commutator, which are these individual segments of copper that are basically connected to each of the turns of winding. Now, the carbon brushes sit inside of this housing, and they're held in here by spring pressure, so that we have constant contact between the brush and the commutator. So as things are turning, the brushes are always in contact with each of the individual segments of the commutator. And there are two brushes involved, one here and one down here. And we can actually see that the wiring is going through the body of the machine and is coming out the face. As we have the turning force, now we're missing a pulley, but we would actually have a device that would be providing us with mechanical motion or turning force to turn and spin the shaft of our generator. And when we have an artificial magnetic field in the field pieces, we have the turns of wire and the mechanical force. What we're going to have is the creation of electricity, in our case, direct current. Now, the brushes are connected through these wires and come out through the face of the machine right here. Now, if I turn this, so the electricity comes out of here, which represents the armature. Now, we actually have to provide magnetism to the machine, and it is said that it takes electricity to create electricity. In our case, we would actually have to provide a little bit of voltage to create current flow within the field windings that are the coils that are wrapped around our pole pieces that are going to create for us that artificial magnetic field that's going to allow us to create electricity. And we're going to require a pulley. I'm going to set this up in one of our training workstations so we can actually see how electricity is being produced. In order to prepare for this demonstration, what I've done is I'm taking a 3-phase alternating current motor, and that's going to provide us with the turning force or the mechanical action for our DC machine. Now, in here is already set up, and you'll see that everything's connected via a belt. Now, inside, what we've got are the pole pieces, and as I mentioned before, what we're going to do is we're going to electrify these coils that are wrapped around the pole pieces to create an electromagnet. So we're going to artificially create magnetism. The motor is going to provide us with our turning force, as well as the armature. Well, that's where our turns of wire come into play. And so when the armature is located in the center of the motor, and we're going to be turning this, what's going to happen is that electricity is going to be created, and it's going to come out through the commutator, through the carbon brushes, and what we're going to do is we're going to wire it up to a DC voltmeter to try and read the voltage. So that's the theory. I'm going to set this aside, and I'm going to start up with our demonstration. Now, before I turn anything on, because of the fact there's going to be a little bit of noise involved, I wanted to highlight that my power supply is going to supply 120 volts AC to my three-phase motor. I'm going to be providing some electricity to create that artificial magnetic field through the variable voltage of my power supply. So you'll see that I can vary the voltage using this knob, and we're going to be using small values of voltage in order to create something over here. Now, I'm going to wire the output. First things first, we're going to set it on the 200 volt scale, and this is DC, and the meter is polarity sensitive. So I've got to make sure we're setting things up correctly. Now, first things first, I'm going to energize the power supply and get the squirrel cage induction motor turning so that we can create that cutting action inside of our DC machine. So now we have cutting action. You'll notice I don't have any output voltage yet because I'm missing one key ingredient. That's the magnetism. I'm going to start to increase the DC voltage, and you'll see it right here as I increase. I got to adjust for the polarity. As we see, if I introduce voltage into the windings, I'm going to create a magnetic field. As I create that magnetic field, you can see that I have an output voltage coming from my generator. Now, I'm providing about 20 volts of DC voltage into this winding, and I'm getting about almost 35 volts. The point is, it's not the voltage, but it's the current flow. If I introduce more current into the shunt field, I'm going to have a stronger magnetic field, and according to Michael Faraday, if I have a stronger magnetic flux, I'm going to get more voltage. So as I increase steadily the amount of voltage and current I'm feeding the shunt field, I'm actually getting a higher output voltage. So we satisfied three conditions. The cutting action that's providing us with the mechanical turning force. I've created the magnetic field by introducing DC current to the windings, and also we've got the actual turns of wire inside of the machine that is actually inducing a voltage, and that voltage is coming out of the armature through the brushes, which we are recording here on our voltmeter. Now, as I decrease the magnetism, but the speed of the motor stays fixed or constant, look what happens to our voltage. So, as I decrease magnetic flux, the voltage from the generator starts to drop. Now, in this setup, I could just as easily start playing with the speed of the squirrel cage induction motor, but that would have adverse effects to the voltage going to my field windings, and I don't think it would really be consistent with the theory. But that's what we're coming down to. I could either alter the speed of this machine, that would affect the output voltage. I could adjust the turns of wire, but from a common sense point of view, it's kind of impractical to try and rewind the motor. It's already been wound. So it's in the textbook, but it's not really a great answer that we could actually adjust the turns of wire, but I could adjust the strength of the magnetic field quite easily by varying the input voltage. Well, I hope you've enjoyed today's demonstration. I really had a good time bringing this to you. I hope it deepened your understanding of how electricity can be created artificially, as well as direct current. Until next time, please stay safe, and if you're enjoying these videos, please consider hitting like and subscribe to our YouTube channel. We have many more exciting videos coming your way.